Okay, so like I mentioned today, it's just going to be chemistry and physics practice passages. If you have any questions, please feel free to put them in the chat. Chris is here with me as well, but I'll also be looking in the chat, and if you want to, please just speak up or raise your hand or anything like that. So consent to audio and video recording. Like I mentioned, this lecture is being recorded and posted onto YouTube. Nothing should be released based about your information, but possibly maybe your name as it appears on Zoom if you ask a question, but we try and edit those out anyway, but just in case you want to rename yourself on Zoom to just your first name or your initials or whatever. Okay, so course description, this is actually the last week of this course, the 15-week course. We still do have the group meet. I still recommend joining it. We have a lot of questions that go even beyond the MCAT, just about the application process. But if any questions you may have on the MCAT, especially since January ones are approaching soon and registration is opening up in a couple of months, November. If you have any questions about anything, it's a great way to get a hold of me or any of the other tutors. There's also a lot of other students there that may be able to help if we're not available. Okay, on to the content. First, we want to do chemistry practice. This passage I got from here. It will be the first link on the Google Drive. I'll also be showing on the screen, but this is the source. I'll give you guys maybe 5 to 6 minutes to read this. Shouldn't really take longer than that. It says originally this passage has 7 questions. If you open up the link, I'll tell you we're not going to be doing all of them. We'll do 4 or 5 for them that I thought were like the best. The others you can obviously, if you want to go on your own, feel free to, but I won't be going over them in this lecture unless you guys have questions about them. I just thought these 4 questions that I picked out were the most high yield, and they were the most like different from each other, and they're like more representative of chemistry as a whole. But take 5 minutes just to read through the passage and kind of familiarize yourself with it. And please put either put like some kind of mark next to your name, like a check mark, or put it in the chat when you're finished reading, just so I know, so I don't waste like extra time. Okay, I'll give you guys maybe another minute. Okay, does anybody, do either of you guys need more time? Or can I move on? Just to the question? Okay. You can always just go back to the passage, and I highly encourage when you're reading these questions, go back to the passage. Okay. This is the first poll question. Start it up. Oh, actually, it's. Chris, could you start the poll? Because I think you have access to the poll this time.
I don't think I have it, Mark.
Oh, okay. Okay, so you guys can just private message me what you guys think is the answer. So that's fine. On Zoom, just private message me what you think is the answer. And that way I'll know when you guys are done as well. Or if you don't know, just message me that you don't really know how to do it, and I'll go over it anyway. So. I'll give you guys another maybe 30 seconds, then I'll go over it. Okay, so the correct answer is B, and I'll go over why. So the main reason that, and you can look if you're all signed in on the Jack lesson, they have their own explanations. I'll go based off the way that I thought about it. So we know that MO is complexed with lysine, right? This involves like knowing the different amino acids. So you have to know what is lysine. It's an amino acid, but more specifically, it's actually a basic amino acid, right? It's a positive one. It's one of the basic amino acids. So because of that, whenever it interacts with something, it acts as a base, right? If the lysine is acting as a base, you need an acid to counteract that. So the MO would be acting as a Lewis acid, right? And remember that Lewis definition, I said it's not super common in my acid base lecture, but Lewis acid just means electron donor or acceptor. That's what the Lewis acid base definition is, right? So in the normal sense, you wouldn't think of MO, especially as an atom, as an acid or base because it doesn't have an OH, doesn't have an H to donate, right? So it's just an atom. But in the Lewis sense, it can act as an acid or a base, and in this case, it does act as an acid because something else is acting as a base. Okay. And these two are not really related. So C and D are those are something different. So amphipathic and amphiprotic, I don't think you'll pretty much ever see anything where that's the right answer. So it's very, very rare that you have to know what that is. Okay. Any questions, or shall I move on to the next question? Okay. If anything, please feel free to ask in the chat or raise your hand or just speak up. Okay. So I think this is actually question 3, not question 2. But I actually like this question a lot. So and remember, you guys can use periodic table, and if you're using the site, there's a periodic table button. Otherwise, you can just look it up on another tab or on your phone. The periodic table is, but yeah. Okay, take another 30 seconds to a minute to answer this question. Okay, I'm gonna give out the answer. So the correct answer is actually A. And this is actually a trick question, which actually did get me when I first saw it. So you may have thought, because MO is an atom, right? And that's what we were talking about in the first question, the MO atom, right? It's the element on the periodic table. This asks, what is the electron configuration of the ion, the molybdenum ion, not the molybdenum atom or the element, right? So first thing you have to figure out is, well, what is the ion? Should have it written here. Okay, so if you go back to the passage, and this is why reading the passage is important, especially when you get caught up on these one word difference, right? In the passage, and you can go back to find this, it says this is the combination. And in this specific combination, lysine is neutrally charged, right? Like I mentioned, lysine is usually positively charged. We know at base pH, it's positively charged. It's a basic amino acid, but here specifically said it's neutrally charged. So that means the two lysines are 0, but the overall charge is +2. So that +2 has to come from somewhere. They said it's not from the lysine. It has to come from the MO, right? That means the MO ion has to be 2+, because this overall thing is 2+. They said the lysine is neutral, so that means MO is 2+. So the MO ion has, because it's 2+, normally it does have 6 more electrons than krypton, right? Or Kr, right? But in the case that it's 2+, it actually only has 4 more electrons, right? So you have to know that this exponent has to be the sum of the exponents has to be 4. 4 obviously works. This one is 1 + 5, that's 6. That would work for the element, and this would actually be the correct answer for the element, but not for the ion. This is 4, so this works. And this one is 3, so this doesn't work in any case, right? So now you have to decide between A and C. Well, remember that the s orbital can sometimes get filled before the d orbital, like in the case of 3D and 4s, right? 4s sometimes gets filled before 3D. However, in this case, it's not as effective to do one. So this is the s orbital, and this is the d orbital, right? It's not as effective to do something like this rather than just doing something like this, where you just fill up the d orbital, right? Okay, so this is actually better. And remember, the d orbital can have 5 in a line, and then it starts to go down, right? So it can have 10 total. But in this case, it would be more effective to just fill up 4 d orbitals rather than have 1 s orbital. So that's why the answer would be A. Any questions about this at all? This one's a little bit tricky, and especially if you really didn't catch this one word that changed the whole question completely. So be careful for that. Okay. Got any questions? Okay, if not, I'll move on to the next question. And I saw somebody else join, so we're actually doing this. This is a practice today, and I gave this passage earlier. It's in the Google Drive that it was linked before, is the first passage. If you want to take some time to read it, go ahead. I'm going to continue with the questions, and then we'll have another passage after this, okay? And then once you're done with the question, feel free to private message me your answer since the poll is not working today, or just write, I don't know, or just wait, no. Okay, so please take a minute to think about this question. Okay, take another 30 seconds to a minute. Okay, so the correct answer is actually C, and I'll go over why. So the first thing thought you may have is hydroxyl group, right? Because you see an OH, you know hydroxyl means OH. So you might say, well, this has an OH, so it must be A. Well, that's wrong because hydroxyl actually means COH, right? So you have a carbon, doesn't matter which carbon, and then it has an OH attached to it. This has an OOH, right? So this is actually a peroxide, not a hydroxyl. So this would not be the correct answer. Next thing you may think of is ether, because you remember ether is like this, right? It's an O surrounded by 2 carbons. Again, this is not the case because it has a carbon here, but it has an OH here. So again, it's a peroxide. It's not an ether, right? It's not an ether because it's peroxides. This group is neither a hydroxyl or an ether. Okay. Next thing is this Tert Butyl, right? And what is a Tert Butyl? Well, it's a 4 carbon, because you know butyl means 4 carbons, and tert means tertiary. So that means it's a carbon that is attached to 3 other carbons. So it's a carbon that's attached to 3 other carbons. How would you attach 3 other carbons? Well, like this. Okay. So, and then you can have one other R group, doesn't matter what group that is, but this has to be a carbon, this has to be a carbon, this has to be a carbon. You see this center carbon actually is a Tert Butyl because it has carbon here, carbon here, carbon here, right? So it is a Tert Butyl. This one carbon is a Tert Butyl. One second, please. Sorry about that. And lastly, secondary butyl, again, same thing. Butyl means 4 carbons, so you have 4 carbons in a chain connected to each other, essentially. And sec means secondary, means kind of the opposite of what tertiary means. So it's attached to 2 carbons, right? So it'll be like this, and then we'll have some R group and some R group, right?
Yes, you could.
Sorry about that. So there's carbon here, right? Secondary, usually secondary you'll see is if you have something like this. And see over here, right? If it's just in a straight line, or actually it needs to draw it like this. Actually, forget this line, but it's if you do it on a straight line, this is a secondary because it also has 2 hydrogens, but 2 carbons. This is a secondary, this is a secondary. This is a primary, right? These edge pieces are primary, whereas these middle pieces are secondary. In this case, this one's a tertiary because it has 3, okay? Any questions about that? Okay, if not, I'll move on to the last question for this passage before we move on to the next passage. And this question is just simply about knowing the different groups, and remember again, OH, yeah. Okay. Last question. This one's going to require a little bit more, I think, thinking and a little bit more like actually drawing out. But yeah, so I'll give you guys a couple of minutes for this one. Okay. And this is from the passage, but this is the step. If you're looking at the passage, it might be easier to see it. There's like a figure that just showed this. I just want to put it here as well for easy viewing. Okay, I'll give you guys another 30 seconds to a minute to answer this. Okay. So the correct answer is actually A. I know if you just look at this diagram that I posted and just think about it this way, you won't really get the answer, but you really have to focus actually on these two things, right? So remember that this happens in 2 steps, not 1. No, it says step 2 here. It's actually 2. Step 2 is actually 2 steps, right? It's not just 1 step. And actually, I think the actual explanation on Jack Weston is really good. So I'm going to actually borrow their diagram, right, in which they show the 2 steps. Okay. So immediately step 1 of step 2 is to go from this to this, right? Right. So using compound 1, which is right here, shown here, right? You can actually turn this, which is what we started with, into this intermediate. And then the second step, you turn that intermediate into something else, right? And that's the product. Okay. So now let's look at this. Oxidation of the alkene and reduction of the alkene. Well, this alkene, the alkene's right here. It's a double bond, right? This alkene, in neither of the steps does it ever get even touched. So automatically, this is wrong because the alkene doesn't get oxidized or reduced, doesn't get touched at all. So those 2 are out. Now it's between A and B, right? Well, like I mentioned, the OOH is called a peroxide, right? So what happens to this peroxide as going from step 1 to step 2? If you just look here, it might look like reduction, right? If you just go like this, I'm sorry, it might look like oxidation, right? Because you're losing an H, right? But it's actually it's hard to see in this. It's easier to see it if you do it in 2 steps. What happens to the peroxide? Well, it turns into OH. What it means is it actually lost an O. It donated an oxygen. Well, oxidation is getting oxygen onto yourself. So giving up oxygen is oxidating something else, right? Because you're giving up oxygen. So you're oxidizing something else. And if you oxidize something else, that means you yourself are getting reduced. That means this peroxide actually got reduced in the first step. And then go from OH to double bond O. I like to remember oil rig. Oxidation is loss, reduction is gain, right? And that refers to hydrogens to protons, right? So since it lost the hydrogen, you use oxidation as loss, so the alcohol got oxidized. There you go. Remember, usually for oxidation reduction reactions, oil rig and calculating the kind of like hydrogens is the easiest way, and that I've seen. The protons or the hydrogens, the easiest way to track their movement, right? But in this case, the first step where you're going from peroxide to OH, you didn't really have any obvious movement of protons. There actually was movement, but it's not as easy to see because usually you track protons through hydrogens and hydrogens weren't exchanged. But remember, obviously, oxidizing, as the name implies, is giving up an oxygen to something else, right? And you know when like iron or something gets oxidized, it gains oxygen, right? Because it reacts with the oxygen. So reduction is just the opposite, just losing an oxygen, because oxidizing is gaining an oxygen, okay? But again, oil rig is generally, and tracking hydrogen is generally the easier way in most cases, but yeah. Any questions about this before we move on to the next passage, or if either of you have looked at the other 2 questions that were in this group and that went along with the patches that I didn't show yet, you want to ask those, you can as well, and I'll go over them. If not, then look at them on your own time and try them. Jack Weston usually has decent explanations, I found. So you should, hopefully those make sense. If not, then you can always ask me at a different time. Okay. All right. If no questions, and feel free to ask me after in the chat anytime, but we'll move on to the physics passage, right? And it's, if you go back to the Google Drive, it will be the second link. Okay. And this one's much shorter, I think, so more straightforward. So hopefully the passage at least is easier to read. I'll give you guys about 3 minutes. Please message me when you're done, or yeah, message me when you're done, or put something up in the chat, like raise your hand or put a check mark or something. Okay, I'll give you guys another 30 seconds or so. Okay, if you guys need more time, please let me know. Otherwise, I'll move on. Okay. So this is a really interesting question. I really like this question. So, because it makes some very interesting parallels between different topics. So take a moment and just message me the answer or anything when you're done. Okay. Okay, take another 30 seconds. Okay. So I'm gonna show result. Okay, so the answer is actually A. And immediately when you see words like parallel, series, you should immediately think of circuits, right? But that's weird. Why, when we're talking about things like flow and capillaries, why are we talking about circuits? Well, if you draw a capillary bed, it looks like this, kind of. Not a great artist, but looks kind of like this. And there's like millions of these like little tubes that kind of like break off, right? Each of these is like its own capillary and like bunch of tubes, right? But you get the point. Well, what does a parallel circuit look like? Well, a parallel circuit, if drawn very simply, looks like this. Right? You guys see how it looks almost exactly the same, right? And remember that a series circuit is just a line, right? Or it's like just a straight line. So capillaries are very similar to parallel circuits. So A or B would be the correct answer. It wouldn't be C or D, right? Because they're not arranged in series. So remember that, and I'll close this and I'll open this. So remember that for the total resistance in a parallel circuit, this is the formula. And then for a series circuit, the total resistance is equal to this. Well, if we were going based off just regular series rules, you would just add them up, add up the resistances of each one, and then that would be the total, right? And that would give you like a pretty high resistance. But they said, why a network capillary is lower than would otherwise be expected? Well, because you're using actually the left formula, right? And that actually makes you have a smaller, total resistance compared to if you were wired in series. And again, remember the main thing about series versus parallel circuits is parallel circuits have many different paths to follow, just like capillaries have many different paths for blood to follow, right? And that's what makes it a parallel circuit, right? So that would be A. As for B, it could also maybe be that because it's also arranged parallel, but it doesn't really increase the total distance which blood must travel, right? And that doesn't really have a big effect on the actual resistance. The resistance is affected by it just being in parallel in general, and because of the nature of being parallel, you're going into different paths, right? If, for example, you took a series circuit and you made it really, really long, so to the point where you're in, the distance is the same as a parallel circuit, the resistance would still be smaller in the parallel circuit, right? Compared to the series circuit, even though the distance is the same for the blood to travel. Okay, that makes sense. Any questions? Sorry. Any questions about this?
Yes, I have a question, Mark. Yes, I understand why it's parallel, but when it's they're going through all these capillaries, are they traveling longer paths since they're going through different paths? So will the distance be longer?
Yes, like I said, technically it is the distance traveled by all the blood. It is technically longer, but like I said, if you had a parallel circuit like this, right? Right, it's kind of short. Then you had a really long series circuit, and then pretend that the distance traveled by all of these together is equal to this really long series circuit. The series circuit would still have a longer resistance. This series circuit would still have a bigger resistance than the parallel circuit, right? So even if you made the distances the same, so technically it is true, but even if you made the distances the same, it wouldn't change the resistance.
Okay.
So yeah, distance doesn't really play a role. Okay. All right. If no other questions, please take a couple minutes to look at this problem. Okay. Everybody's ready. Right. So the correct answer is actually D, increasing hematocrit. So this actually really didn't involve that much thinking. This actually was just based solely on the passage, honestly, because they gave you the equation for Reynolds number, right, RE, and its density, viscosity, velocity, and diameter, which is basically the same thing as radius. And said if the Reynolds number becomes too high, so if RE goes up, a fluid is more likely to become turbulent from laminar, right? And that's which of these is least likely to result in going laminar to turbulent? Which of these is least likely to increase Reynolds number, right? Which of these will not increase RE? Well, decreasing the viscosity is over here. If you make the denominator smaller, it'll make the whole number bigger, right? Because if you're decreasing the velocity or just decreasing the denominator, it'll obviously make the end result bigger. So it's not this. Increasing blood velocity, well, velocity is on the numerator. Increasing something on the numerator will make the number bigger. So not B. C, increasing blood vessel radius. Radius is essentially diameter. So increasing diameter, again, in the numerator, increasing the diameter will make Reynolds number bigger. So it's not C. Hematocrit, you kind of had to know it, but really you could do it from process elimination. Hematocrit is a protein that's found in blood, right? And it says the viscosity of blood is largely determined by the cell protein contents of blood, right? So increasing the hematocrit would kind of increase the viscosity, right? And if viscosity is increased, then if the denominator gets bigger, the whole number gets actually smaller. So it would not really increase Reynolds number, which would not have laminar turbulent transition. It's because that D is right. Any questions? Does that make sense?
Yeah, I was thinking hematocrit was like you said, protein. So if you're adding more protein, you're making it thicker, and thicker is gonna add more turbulence. So hence
Yeah, exactly.
hence why it says
Yes.
least likely to cause. It's causing more turbulence, and the question is wanting the one that does not cause turbulence. See, am I reading the question incorrectly? The question is asking for the one that does not cause turbulence.
Exactly. Yeah, which is least likely to turbulence, but you have to like read the passage. Don't go too much into like your own knowledge for at least this question, because look, it says if the Reynolds number becomes too high, a fluid is more likely to flow in turbulent manner. So what causes the transition is actually increasing the Reynolds number or increasing the RE, and it gave you the equation for RE, so you can find out exactly what would make it more or less turbulent.
Reciprocal relationships. Okay, got it. All right, thanks.
Yeah. Right. So just be careful with that and try and look out for anything that might in the past that might help you. Any questions on that one before we move on? Not, then take some time for this question.
Mark, do you mind popping up the compliance equation real quick again, so I can see what kind of relationship, if it's exponential or it's linear, or
yeah, they did. Here, I'll just pop it up real quick.
if you
but
could just
yeah,
pop it,
if you want to go to the Google Drive, over here, it's right here.
Okay, compliance is C. Okay, let me just write it on real quick. Delta V.
Yeah, it's just delta V over delta P.
And the V is the volume and P is pressure. Okay, get back to the graphs.
Yeah, I'll just right here if you want.
No, which graph represents this? Which graph?
Okay, is everyone ready? Okay, so the correct answer is actually C. And for this, yeah, okay, so I'll go back to the passage just to highlight something. So the most important thing that you should have gotten is C is the compliance. At low pressures, veins have a greater compliance than arteries, right? And it tells you why, but not important. At high pressures above 20, compliance becomes nearly equal between veins and arteries, right? So at low pressure, veins have bigger compliance. When you get to high pressure, they have the same compliance. Keep that in mind. Now, like I mentioned, what is compliance? Well, compliance is delta V over delta B, and V should be delta, right? And in this graph, what is delta V? So if you notice the y-axis is V, the x-axis is P. So compliance is actually just the slope of each line, right? And what it said was the compliance of a vein is high at low pressure, so it should be a very steep slope. And then it lowers out when you get to higher pressure, lowers out and becomes the same as an artery. So let's say arteries are like this, and we'll pretend this like the same line right here, right? So it looks something like this, which goes along with C. Let's look at the other graphs first, right? So this one is just one line, right? So this says just arteries have a higher compliance than veins at all points, right? Because their slope is always steeper than veins at all pressures, which is not the case. It's actually the opposite, and then it evens out. But this is wrong because this graph shows arteries having a higher compliance than veins at all pressures, all x values. So not A. B. Well, compliance doesn't actually. So again, I mentioned compliance is slope. Well, arteries have a negative. Here, this is a negative slope. So it never mentioned that they have a negative compliance, right? They have maybe a lower compliance, but that doesn't mean negative, right? So because it doesn't have a negative compliance, B is out because there should not be any decreasing anywhere or going down. As for D, so D has it might seem like the right answer at first because look at high pressure they actually even out in terms of physically they even out. However, if you notice, like I mentioned, compliance is the slope. The slope over here is very small, very, very, very small. The slope here is just constant, whatever, right? Very small is not the same as just constantly increasing at a good rate, right? So the compliance itself, the slope itself, is not equal, right? The y values, the pressure or the relative volume, actually might be equal at the end, but the actual slope, the compliance, which so we're looking for, is not equal. However, with C, if you notice, above 20, which is about here, this slope, they're relatively similar, right? They're increasing at about the same pace. They're almost like parallel lines at that point. Not exactly, but it did mention they become more equal, right? Not 100%, but it's close enough, and it's the closest that we have. Whereas initially, veins have a much higher compliance at low pressures, right? And that's represented by arteries having a very small slope, whereas veins have a very big slope here in the beginning that evens out. Does that make sense? So somebody asked in the chat, this part, just up until here, or actually just this whole artery thing, it shows a negative slope, right? The slope of this artery line is a negative number. It could be, at this point, it could be like -5, and then it goes down to over a gradient to -1, right? That means the compliance, according to this graph, of an artery is C equals -5 going down to -1, right, on a gradient, right, because it changed. But they never mentioned that the compliance in the passage never mentioned that the compliance was negative or that it even could be negative, right? It mentioned that it was smaller than that of a vein, but it never said that it was negative.
I'm
Right.
sorry, Mark,
So
but it's not showing negative. We just went from 5 to like 1.7. Where are you seeing negative?
Right. What's so here? I'll give you another graph that's easier to see. So let's say this one is 3, this one is 1, this is 2, and this is 4. Right. From here to here goes like this. This is a line, right? Went from 3 to 1 over a 2-second span. What's the slope m of this graph?
3 over, okay, 3 minus 1, that's, what is 2 over 2? 1?
This, do you think the slope is 1?
Y over x, right? So the y is
Yeah.
3 minus 1, which is 2, over x, which is 4 minus 2, which is 2. 2 over 2 is 1.
But it's not 3 minus 1, it's 1 minus 3 because it's final minus initial. It's changing. So
Oh,
it's
yes,
final minus
yes,
initial.
yes. Okay.
So what's the
yeah.
slope?
1 minus 3 is 2 over 4 minus 2 is, I'm still, 1 minus 3 is okay, -2 over 4 minus 2, which is 2. So -2 over 2 is -1. Am I correct?
Right. Slope is -1. If the line goes down, that means it's a negative slope, right? You can see here the line is clearly
fine.
going down, right?
Final minus
So the
initial.
slope is
Okay.
yeah, so it's negative, right? And we mentioned that slope is equal to
Okay.
compliance. It means compliance negative, right?
Okay, it's final. Okay, I was doing the backwards. All right, got it.
Yeah, no problem. Okay. Any other questions before I move on? I believe this will be the last question. Yeah, this will be the last question. Any questions about anything before I move on to this final question? If not, then please get started. If there are, please ask me in the Okay, take another 30 seconds or so. Okay. If everybody's ready to go over this. So the correct answer is actually A. And I think the main thing to note in this problem is, again, reading the problem and being very careful with the wording. So what is it asking for? So person, they're measuring at the shoulder and at the wrist. And so two different spots. And then they had them raise the arm straight up and then hold it straight down. And then they measured the difference in pressure between the wrist and the shoulder in both positions, right? So they want to know the difference between the differences, if that makes sense. So the difference between the head and shoulder measurements is delta P, right? It's the difference between the wrist and the shoulder in one position. So the difference between the hand and wrist when it's up versus the difference between these two when it's down. And again, I think Jack West had a really good diagram to explain this, right here. So they want this difference versus this difference, not the difference between the shoulder and the wrist, the difference between the difference, right? That kind of makes sense, right? So this delta P, right, versus, so delta PU, which I'll say is when you're going up, and delta P versus delta PD, which is when your arm is down, right? So there is now a delta P, but there's also, I guess if you want to think of it, a delta P. Right? And the delta P is what they're asking for in this question, right? And the difference between these two differences should be equal in both positions, right? And you can see that here. What is delta P equal to? Delta P up. Delta P up is equal to
Rho GH, or?
Yeah, exactly. Rho GH. Well, rho G delta H actually, because remember height is relative. Everything is we can set a zero really anywhere. Rho G delta H, right? And it's written here as well. And rho is whatever the blood density is. We don't care. It's the same no matter which position your hand's in, which part of the body, and the density of the blood is the same. We're assuming G is also the same. Doesn't matter if your hand's up here, up here. If you're looking at the shoulder, the wrist, G is always the same. So these two don't really matter. We're only really looking at delta H. Well, if your hand is raised, the distance between your shoulder and your wrist is, say, in here they use 60 centimeters, right? That's the length of your arm. Well, if your hand is down here, the difference between your shoulder and your wrist is still 6 centimeters because that's the length of your arm. The length of your arm doesn't change if you're doing this or this. Your arm is still the same length, right? So delta P D, which is when your hand is down, is also equal to rho, which we mentioned. Rho is the same no matter what. Rho is always the same. G, again, always the same. And delta H. Delta H is just the length of your arm. Again, length of your arm doesn't change if you're doing this or if you're doing this. So the delta H's are the same. So we can just cancel that out too. And you're just left with delta P when your arm is going up is the same as delta P when your arm is going down, right? It's that simple. Now let's go over why the other choices are wrong, okay? Greater when the arm is held in the air due to greater fluid potential energy. You may get confused by thinking, well, if you're putting it higher up, you have more potential energy because that's usually how it works, but that doesn't really make sense with kind of the pressure differences, especially with like potential energy. It's doesn't really make sense. So I can't really explain it too well because they're not related concepts in a way. So it's kind of really hard to explain. But if you were to increase like the height, it doesn't matter. It's just the height difference between your shoulder and your wrist, if that makes sense, not the actual like total height, because otherwise it would matter if you're standing on the first floor of a building or on like the 10th floor of a building. Your blood would be completely different, and like it would be your blood pressure would be completely out of whack depending on which floor of a building you were on. If you were living in a city that was on sea level versus a little bit above sea level or below sea level. So we never really like look at actual height. We look at relative height. If that makes sense. greater when the arm is held in the air due to increased height. Again, so that's the same thing. It's the same logic. It doesn't work because we use relative height, not absolute height. Otherwise, if you were standing on the 10th floor of a building, your blood would have insane pressure, and it would just burst or whatever. Whereas if you were standing on the first floor of a building, your blood would be like pouring out or something because it has no pressure. Right, so we use relative, not absolute. And the lower when the arm is held in the air due to reduced hydrostatic pressure. Again, hydrostatic pressure is kind of the pressure that's inside your body, right? Near your vessels. That doesn't change depending on the height either, because it's your hydrostatic pressure is very heavily controlled by things like proteins, by like just everything in your body is just controlling the hydrostatic pressure around your veins, so it doesn't really change with height. So it wouldn't be D either. Does that make sense? Any questions about this or anything else that we've covered so far today?
Yes, Mark, could we have figured A, since you just said, since hydrostatic pressure almost has to do with, like you said,
well, hydrostatic pressure is the kind of the pressure kept by your body. It's not inside. So your blood pressure can change, right? Your blood pressure does sometimes change. It's not, your blood pressure is not the same as the hydrostatic pressure.
yeah, what, so you're telling me if I worked on a skyscraper on the 10th floor versus if I was on a ground floor, that I'm gonna have, and somebody took my blood pressure. I'm trying to understand relative pressure.
It would be the
and
same.
absolute-
The blood pressure difference between your shoulder and your arm would be, and your wrist would be the same. Yeah.
Oh, because of the same.
And that's why B and C are
hydrostatic
wrong. Yeah, that's why B and C are wrong.
Oh, okay.
Because it wouldn't be
Hydrostatic
different.
Relative and absolute. Yeah, you just throw out some words there. I was just like, yeah.
Yeah.
It's a relative
yeah.
term versus absolute. Okay. The question I had was the one about the outside information with the Reynolds number that was given in the passage, correct? So
Yeah, that was given in the passage. I just put it on the slide just to make it easier to see, but it was in the passage if you look back.
Yeah, so it's not okay to, yeah, so it's better. Yeah, I don't know why I was using outside knowledge, which change is least likely to result in laminar flow. I automatically started thinking about, Pucelli's and that Ventura effect. I read it somewhere earlier.
Right.
And so how do we know not to bring in, like, if it's a discrete question versus something in the passage? How do we know not to, because clearly I immediately start saying, oh, this is something discrete that as a head knowledge versus a going back in the passage. So how do I know not to do that?
Right, and that's one of the advantages of reading the passage carefully the first time rather than going straight to the question and then going back to the passage that I found, especially for bio and chemistry and physics, is because pay attention to what they tell you in the passage. Like, for example, I don't know what turbulent flow is. Like I've heard of it before, but I don't really like exactly know what it is. But when I was like, I remember when I saw the question, I was like, oh, I read something like this here, right? And I went back to the passage and I'm like, oh, there it is. And then I kind of read it carefully again. And that excerpt that I posted, I think I posted this excerpt right here. Yeah. I literally went back, scanned the passage, and I found this exact excerpt. And then I was like, okay, well, this has to be the answer. And I used this to answer it, right? So it's kind of, sometimes you have to use outside knowledge, sometimes you have to read it. It depends on, like, you have to see if you can find it in the passage, if you remember reading something like that in the passage. And if you do, then go back to that. If you scan the passage again and you read it again, you're like, it's nowhere here, then you have to use some outside knowledge. Right? Something like this, like laminar turbulent transition, this is not like tested like ever. So it's really safe if you see something like this to be like, they must have mentioned it somewhere.
In the passage,
and like,
right. Oh,
yeah.
okay.
Yeah.
So if it's
they mention something simple like lysine,
Yeah, so it's something like the average MCAT taker wouldn't necessarily know offhand. It's possibly back in the
Exactly, yeah.
past. Okay, good. And if one other question, I joined just when you started going over the electron configuration and ion versus. So what if it's sometimes I have trouble when they say, like, for example, something simple as sodium. When it's in the ground state versus when it's in the ionic state. Is there a trick to these to working when it's ion versus non-ion, like it's like this
Yes.
molybdenum ion versus if it's a regular molybdenum, what would that look like?
Right. I believe MO, like just the element in the periodic table, has a number of 42, right? And you can double check that, but I'm pretty sure it's 42 because I looked into it today. And I was like thinking this lecture. So
Okay.
42. Do you remember? You know what obviously an atomic number means? That's how many protons and how many electrons
correct.
MO has, right? In its
Yes.
normal state.
Yes.
Well,
I know.
yeah, electronic configuration is the configuration of electrons. You know, normally it has 42 electrons. That means when you do all of the electron configuration stuff, like the 1s2, 2s2, 2p6, all of the exponents have to add up ultimately to 42. They usually make it easy, so you don't have to write 1s2 and whatever. Every time they write have
they go to
the
the
last one.
Yeah, they go to the what is it? Those elements on the
noble gas.
Noble
Yeah,
gas.
yeah.
Right. I got that much.
Yeah, it goes to you're right. So and you know that the noble gas Kr is 36, right? It has an atomic number of 36, meaning it just writing Kr counts for 36 of the 42 electrons.
Perfect.
So all you're left with is just accounting for the last 6 electrons, right? And you have to find out exactly how the last 6 are ordered. But again, it's really easy because this one has 4, this one has 4, this one has 3, this is the only one that has 6, so that must be B, right? But they asked, that's for the atom, but they asked for the ion.
So B would be the correct config for the atom.
For the atom. Yeah.
Okay, got it. Let me just
but they said ion. The ion that we're looking at is specifically MO2 plus. Well, what does 2 plus mean? It means it has 2 more protons than it has electrons. That's why it's positively charged. You can't add more protons, otherwise you change elements. So it still has 42 protons. The only way for it to have 2 more protons than electrons is if it now only has 40 electrons. So now MO2 plus is actually MO40 electrons, not 42 electrons like the atom, right?
But
does that make sense?
But don't we change it when we change the number of, only when we change the number of protons, we change the atom. But changing the electrons,
right? Yeah. So if you had 43 protons, it's not MO anymore. It's a different element.
So we can change
electrons. But obviously, you change electrons all the time. That's how you get ions. So MO2 plus is actually MO with 40 electrons. Again, just writing Kr, you're accounting for 36 of the 40 electrons. So now you only have to make up 4 more electrons. There's multiple ways to do that. Here they have A, this one is 4, this one is 6, this one can get canceled out. And we already mentioned that's for the element, not for the ion. This one has 3, so it also gets canceled out. This one also has 4, S1, D3, or 44. It's now 50-50 between A and C, but I told you that A is better than C just because sometimes you want to fill up the S orbital before the D orbital. This is usually filling up the 4s before the 3d. But in this case, you would want to fill up the D first just because you only have 4. So for these elements, you fill up the D first.
Which rule is that again when we fill out the S before the D? Typically, we'd want to fill out the 4s before the D, but this case we
before
do
the 3D, right?
Before the 3D.
I'm not sure I don't know what it's called. That's just how I learned it. It goes here. I'll actually write out 1s2, 2s2, 2p6, 3s2, 3p6, and then instead of 3d10, it goes 4s2, 3d10.
took a picture of that. Mhm.
then 4p6.
Wow, so that's gonna be helpful.
Right, and this is, by the way, this is actually this is KR. So I just wrote out KR, and it's specifically in this order: 1s2, 2s2, 2p6, 3s2, 3p
6.
3p6, 4s2,
Yes.
3d10.
Mhm.
Oh, I missed the 4s2 actually. Oh
So
no,
that's
I
the
did it.
KR, but we're still accounting for the last 4 because we're up to 30.
Right, and then we're just
So-
and then we're just continuing from here, right? We have the 4p6. Now we're just continuing from here now. So the next one would be either 5s2 or 4d10. But we're filling up the 4d first before we move on to the 5s in this case.
Okay. Fill 4D
If you
first.
have something actually like this, the reason is, and remember that, so like a d orbital looks kind of like, it looks like a box. 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5. Right, it has 5 things. So because it can have 10 total, it has 1 up, 2 up, 3 up, 4 up, 5 up, then 6 is down, 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 down. All of the orbitals are like this. So like the S1 is just one box and goes 1 up, 1 down. Right, if you remember that.
Yeah, Hans rule, you
the-
want to fill each shell first before you take on another roommate.
a second one, you're right.
Yeah.
But and the reason this is really good is because this actually 4d5 5s1 is because you have 1 in here going up, and then you have all 5 of these with 1 at least, and then you rather than doubling up beforehand. So that's why B is really good for the element. But since we don't have enough electrons for that in this case, and for the ion, we use A instead. So I can actually